and in the continuation with the faculty development program in emerging trends in the machine learning. So we are starting with the second session of day 5. So the speaker for this session is Dr. Ajay Kumar. And first of all, I would like to give brief introduction about him. Then we will continue with the session. Dr. Ajay Kumar, currently working as the Associate Professor in the Department of Computer Science and Engineering, Thapar Institute of Engineering and Technology, Patiala. He has 17 years of experience in teaching and research, and he has done his PhD in practical computer science and from the Thapar University, Patiala. He has completed his MTech and gold medalist in computer science and engineering from Kurukshetra University, Kurukshetra. And he has handled number of research projects and under the title development of a tool in the aid of patients suffering from amyotrophic lateral sclerosis using the developed low-cost eye tracker by the DST. And he has done number of certifications in the quantum internet and quantum computers. How will they change the world? By the Deptt University edX online course, and by the building blocks of quantum computer by the Deptt University edX, and introduction to quantum computing by MIT, and understanding quantum computer by KO University. He is guiding 3 PhD scholars, and 3 PhD completed and 4 PhD are pursuing, and almost finished the 40 MTech thesis guidance and supervise the 40 MTech thesis. And he has almost 55 research publications in the national and international journals. And his main area of interest is the quantum computing, automata theory, and software testing. So with this brief introduction, now I would invite our today's guest, Dr. Ajay, to continue with this session. Over to you, sir.
Thank you, madam. I will take 1 more minute.
Okay, sir.
So I'm sharing my screen.
Yes, sir.
Is it visible?
Yes, sir. Visible, sir.
So you can call it as a session for, you can say building blocks. You can call it as building blocks for quantum machine learning.
Okay, sir.
So I will not cover too much topic about quantum machine learning, but these you can consider as a basic fundamentals if you are interested to learn something about quantum machine learning. So I will start with few concepts that what is quantum computing and why it is important. So we can call this quantum computing as a combination of 3 subjects. You can call it as mathematics, physics, and computer. And what are the basic requirements you will need to understand these concepts? You must have a good knowledge of linear algebra, some concept like algorithms and its complexity, and then if you are familiar about circuit, like we are creating half adder, full adder, or you are familiar about sometime you are familiar about AND gate, OR gate, NOR gate, all these kind of gates. So let me start why we are interested in quantum computing. So we have 2 important algorithms that are developed. One is known as SOR algorithms. And the second one is known as Grover algorithm. And there are other algorithms also available in the area of quantum computing, but these are the first 2 algorithms after which there is a rapid interest of pupils in the area of quantum computing. So what is use of quantum Grover algorithm? You can call it as like we are performing linear search, binary search. So in case of linear search, we are searching element one by one and until we will found the element. So its complexity is order of n. Like if we have a list of elements, suppose we have n number of elements and we want to find out, let's suppose 11. So we will compare element with this one, then with 8, then 7, then 9, and then 11. In worst case, we have, if we have n elements, so we had compared our elements that we want to find with all the elements. So its complexity is coming out to be ON. As compared to this one, if you observe binary search, in case of binary search, list must be sorted. Means either elements are increasing order or in increasing order or in decreasing order. So if we want to search an element, like let's suppose we have these elements. And if I want to suppose I want to search an element like say 250. So first I will take half of this one, that is 512, and I will compare my element with this one. Now 250 is less, so we will search in this part and so on. We will repeat our process, and in log 2n times we can able to find out our element. Find our element. So if we have 1024 elements, so maximum it will take 10 iteration to find the elements, because log 2n is 1204, and you can take it as log 2 raised to power 10, and it is coming out to be 10. But if you observe the Grover search algorithm, although we will not discuss the complete algorithm, but what it will do, it will find out unlisted element in this much time. That is order of n square root. So it is an improvement over the classical algorithm. So this is one of the advantage of quantum, that it will support us some algorithms by which we can able to perform something better in a better way or efficient way. Second, you can call it as second algorithm, you can call it as a SOAR algorithm. And all of you are familiar with this concept that RSA algorithms is based on finding prime factors of a large number. So any security algorithms are based on these type of concept in case of classical computer. Let me take some example, like if I give you any number like this one, so you can able to find out its prime factor, like 257 multiply 977, but it will take some time. Now number of digit in this case is 1 2 3 4 5 6. If I give you 9-digit number, let's suppose I take this one, so it will take more times. And let me compare a 10-digit number, and if I want to divide this number n into two prime factor, let's say prime 1 and into prime 2, can you relate how much time it will take greater than 9-digit number? So whatever 9-digit number will take, multiply square root of 10, that is approximately 3 times. So if I divide a 9-digit number into prime factor, and if I take a 10-digit number, it will take around 3 times more time as compared to the 9-digit number. Let me take 100-digit number. So it will be 10 times harder than 10-digit number, because it is multiplied by 10 and so on. So dividing a large number into 2 prime factor is a exponential problem in classical computer, whereas the same task can be carried out in polynomial time in quantum computers. So after 10 or 15 years, whenever we have quantum computer available to us, we can able to find out large 100-digit numbers in polynomial time. Now, these are the two main reasons why people are working on the area of quantum computing. So let me start with few fundamentals. Like in classical computing, we are using bit. Here we will use quantum bit. And we will also call it as qubit. So we will also create qubits in IBM quantum computer. So that is available online. So we will work on that particular case also. So bit, you are familiar with this one, that it is denoted by 0 or 1. I can denote it by a vector 1 0 also. I can denote it by 0. What actually it means? 0 bit, I can represent it by a vector containing 1 column and 2 rows, and this 1 indicates that 0 is presented. This 0 means 1 is not presenting. This 0 means 0 is not presenting. This means 1 is presenting. So in the first case, 0 is presenting with probability 1. In this case, 1 is presenting with probability 1. You can call it as like this one. But in case of quantum bits, we can have both the possibility that we can in 0 state as well as in 1 state. So it might possible that we are in having these kind of things. So this is a, let's suppose I denote it as a qubit. It is denoted by these kind of sign. It is known as cat notation basically. So it is denoted by alpha beta, and I can call it as alpha 0 plus beta 1. So what I can denote, that the probability that we are in 0 state, that is alpha square, we will discuss it. Probability that we are in state 1, that is beta square. And these alpha and beta can be complex number also. Can be complex number. You can understand it by this way, that let me take 0 state in this side and 1 state in this side, and I can denote a vector alpha 0 plus beta 1. Let's suppose this is alpha, this is beta. So there is a point alpha beta. And I can represent it by vector this one. So this is our psi, you can call it as psi, and if this is psi, this will become alpha, this will become beta. Now, what is the probability that we are, if you measure this amplitude, what it will come out to be? Using Pythagoras Prameya, you can take it as alpha square plus beta square, and it is coming out to be 1. If it is a valid qubit. Valid qubit. If it is not a valid qubit, then its amplitude may come out to be 2 or half or something else. But in case of it is a valid qubit, its amplitude is coming out to be 1. So what is the probability that we are in 0 state, that is alpha square, and what is the probability that we are in 1, that is beta square, and the total probability will come out to be 1. And one more thing, alpha and beta can be complex number. So in case of complex number, you are familiar with these kind of things, that it can be determined by complex conjugate alpha into alpha conjugate. Let's suppose alpha is 1a plus b iota. So it will become a plus b iota into a minus b iota. Rather, you can multiply them and you will get the result. So let me send you one link where you can create your account first, and then we will discuss the concept of how you can able to create your qubit. So I'm sending a link in the chat box. You can just go to that particular page and create a link. So you can create your account on this particular link. This is nothing but it is a quantum computer that is provided by IBM, and you can able to work it online. So first you can create your account. And what is the process to create an account? You can just click on the link, and then you can create a new user. And once you create a new user, you will find out these kind of thing: launch.
Sorry to interrupt you, sir, but screen is not visible, sir.
Okay. Let me share. So you got the link. All of you have received the link, na?
Yes, we have got.
Okay. I will give you 2 minutes time. You can create your link, and then we will move ahead so that we can able to discuss how you can write down few programs or how you can able to create the qubits. So once you create your login, you can just put a message in the chat box, then we can start again. And we will start with launch manager. There are two options. One is IBM Quantum Composer and second is IBM Quantum Lab. So we will start working with IBM Quantum Composer. So you need to just click on the concept of launch composer.
Sure, sir. Go ahead, sir.
You can take 2-3 minutes time to create the login, and then
Okay.
we. So once you create your login account, then just click on the launch composer. So we have basically two options. Let me write it over here. IBM Quantum. Launch composer. And second is launch lab. So this is basically Qiskit programming, you can say. And here what we can say is we can use the option of drag and drop. And second, we can write down QASM, that is quantum assembly language. I hope everyone has created the account. Okay, so we can move ahead, and let me click on the launch composer, right? So if you click on this one, you can able to see my screen. There are 3-4 things visible to you, right? One is in the left hand side, you can find out that there is a composer file, and in between there is a circuit, and in the right hand side, if you will observe, there is open QASM 2.0. So that is the concept of quantum assembly language. So let me create a new circuit. New circuit you can able to create, go to the file and just click on new. So whenever we will click on new, you can easily able to say observe that there is 3-4 lines of code will be created by default. It include one header file, that is qlib1.inc in the right hand side. Then there is a concept of qreg. Qreg is nothing, it is quantum register, and that's name is q, and you have given 3 qubits. So I have created 3 qubits, and it's stored in a quantum register, and that's name is q. So in the diagram, you can easily able to observe q0, q1, q2. If I change the value, like if I say 1, so you can easily able to say you observe only q0. That is quantum register name q with only 1 qubit. Similarly, creg, that is quantum register, sorry, classical register. Its name is C, and there are 3 classical bits. So let me change it to 1. Okay, all of you, I assume, are familiar with NOT gate, right? So by default, qubit is in 0 state. I can write down the coding using drag and drop operations. Like I have dragged the operation NOT. Its name is NOT. After H, there is one gate name as NOT, second gate. So just drag and drop it. You will find it on the screen. And corresponding to that, quantum assembly language will write down a line X gate. They will call it as X. And on which qubit you are applying it? On Q0. That is on the first qubit. Right? If you have any doubt, you can just send me the message in the chat box. So we had created a circuit that includes 1 qubit in a register named as Q. Another is classical bit I have created, and that register name is C. And I had applied a X gate, or you can call it as NOT gate. What is purpose of NOT gate in classical computing? That it will change 0 into 1 and 1 into 0, right? So there is an option, file, edit, inspect. So if you go to inspect, you can able to observe the result. Because in this only a single circuit is there. So later on we will use this facility. Let me take. In the right hand side, if you observe, there is setup and run. On the rightmost corner. Let me click it. And what you will find out, just drag and drop over here. If you observe the name like IBM QASM simulator, simulator underscore state vector, and if you drag and drop it, you will find out a large list of simulator and actual IBM hardware. Like last one is IBM underscore Centigo. So you can easily able to observe the number of qubit this hardware is providing. Like Centigo is providing 5 qubit. State simulator will provide 32 qubit. QASM simulator is providing 32 qubit. So by default, you will find it is QASM simulator, right? So if you observe, there are total pending jobs are 3 or 2, because a number of persons are running it online. So it is having 32 qubits. Let me simply run it, run on IBM QASM simulator. So I can able to observe my result over here. You can go to view all job also. Let me take once again, setup and run. Okay, before running any simulator or any circuit, you need to measure it, right? So for measurement, there is an option in the second row, and I will just drag and drop it, this one. So it is nothing, it is measurement in G basis. And whenever you want to measure any qubit, it is measured from quantum qubit to the classical qubit. In the right hand side, you can observe that it is a measure from Q0 to C0. And now I can able to run it. Now, if I run it, I can able to find its result over here. This is pending job, and it is indicating the end time 2:31. And once it is completed, it will show us the result. Let me click it and observe. And it is denoting all these details that it is in the running state. Now it is completed, and you can easily able to observe the details. And what you can observe over here, that is frequency that we are getting one is 1000. So whenever we are running any quantum computer program, we have to run it a number of times, and by default this time we are running it 1000 times. We will discuss why we need to run it more times after discussing the Hadamard gate. So in all cases we are getting the result as 1. So why we are getting the result as 1? Because qubit initially is in 0 state. We had applied NOT gate, and if we will measure it, we will get the result as 1. Right? Let me show you again why it is showing the 1000 results. Because if you observe over here, number of shots, it is indicating 1000. Right? We will discuss why we are running it more than 1 times after discussing the Hadamard gate. Are you able to create this kind of circuit? If you have any doubt, you can put in the chat box so that we can discuss. Yes, any question so far? So far what we had done, we had created a circuit with only 1 qubit, and we had applied the simplest gate, that is NOT gate, that you are using in your classical theory also. Let me stop it a little bit, and we will discuss first the concept of Hadamard gate, and then we will come back to this one. Now, I think all of you are familiar with the concept of random number. In C or Java, you are creating your random number using array ND function. And there you will provide some initial seed also. And you will also provide your range, that you want to generate a random number between 0 to 1 or 0 to n or 0 to 50 or whatever it is. Now this initial seed is like, if I want to generate a random number from 0 to 1, maybe initial seed is 0.5. And you generate these random number, like first is 0.5. You apply some function, next random number may be 0.7. Next will be might be 0.3. It will be 0.4. It is 0.9. But these are not the actual random number. These are pseudo random number. It means if anyone is having this seed number and this range, he can able to generate 0.7 from 0.5 if he or she knows the actual function. From 0.7, he can able to generate 0.3 and so on. Because 0.9 is dependent upon 0.4. 0.4 is dependent upon 0.3 as well as some function. So these are interrelated. Means these are not actually true random number. So these are pseudo random number. So if anyone is aware about the seed and the function, he can able to generate the same sequence. So what actually random number is? Random number means if there are two persons, let me take X and Y, and if he want to generate some sequence, so might be 0.5, 0.57, 4, 6, and the other person can generate these kind of sequence. And the second important point is this number 0.5 should not be dependent upon 0.3, 0.7 should not be dependent upon these two numbers, and so on. Then we can call these number as true random number. Right? So we will generate true random number using quantum computing today. Let me take a gate, Hadamard gate we will use. Now, first I will tell you what is the meaning of the Hadamard gate. And I think all of you are now familiar with this concept. This is the cat notation. Whatever I will write down in this one. So our cat initially is in 0 state. So 0 state is represented by this one. Cat in 1 state is represented by this one. And what is meaning of a Hadamard gate? Hadamard gate is represented by this matrix notation. So every gate can be represented by a matrix. Like if I write down the X gate, and we will discuss it again, or NOT gate, you can call it as 0, 1, 1, 0. That we had discussed earlier. So if I give qubit in 0 state, what it means? If I multiply it, it will be 0, it will be 0, and it will be 1, and it will be 0. So we will receive our qubit in 1 state. So if I apply 0 to X, I will reach into 1. Similarly, you can observe if I apply 1 to X, I will reach into the 0 state, right? What will happen if I apply X and X again? I will reach into the 0 state, because at this point of time, I will be in 1 state, and then I will reach into the 0 state after application of another Hadamard gate, right? Now, this is the matrix notation for Hadamard gate, and it is used to generate true random number. Now, let me take my qubit is in 0 state, and let me apply the Hadamard gate, and what we will get. So this is my Hadamard gate matrix, and the qubit is in 0 state. So I can denote it by 1, 0. Just multiply it. What we will get? 1 by square root of 2, 1, 1. I can denote it by 1 by square root of 2, 0 plus 1, because this is denoting the 0 state. This is denoting the 1 state. So if I apply Hadamard gate on 0 state, what I will get is this one, right? Second one, if I apply Hadamard gate to 1 state, what will happen? Let me take 1, apply Hadamard, and what we will get? That we will implement practically on the Qiskit composer also. So you can multiply it. So you will get 1 minus 1, and this one is the case. Now, can you tell me if I measure it, what we will get? On 0 state, if I apply Hadamard gate, what I am getting? This state. If I apply Hadamard gate on 1, I am getting this one. Listen one thing very carefully. Now our qubit is in 0 as well as 1 state. Agar ye hamari state thi initially, so we will get this result. And by this result, what we can say? Probability that we are in 0 state. What is the probability? That is 1 by square root of 2 square, that is half. Probability that we are in 1, that is also half for this particular case. right? So probability that we are in 0, that is half. Probability that we are in 1, that is also half. So whenever we will measure it, either it will fall into 0 state or it will fall into 1 state, right? So if we will run this circuit 1000 times, what are the chances? That around 500 times it will give us 0. Around 500 times it will be 1. Right? That's why we are running our result. Because if we run it only once, what will happen? We will either get the result as 0 or 1. But if we will run this result 1000 times or 500 times or 600 times, we will get half of the time as 0 and half of the time as 1. Right? Now, how you can say first time what will be our result? What is our first time result? It can be 0 or 1. For someone running it first time might get 0 and other may get 1, right? And it's totally you can say totally independent. So you will get a complete sequence. If you run it 1000 times, you will get a complete sequence 0 1 0 1 0 0 0 0 1 1 1 1, something like that. And this sequence is totally true random number. What you can call it as true random number. Now let me try out the same thing on IBM computer. So you can just go to this one and let me first remove this X gate because we will only require Hadamard gate now. So you can just go to the right click on this one and you can cut it, right? So initially this is our circuit. So simply drag H gate and then let's suppose measure it, right? So correspondingly coding will be changed as HQ0. So Hadamard gate is applied on first qubit and then we are measuring from Q0 to C0. And let me run it once again, set up and run, and its number of slots, let me take it as 1200 and let me run it. So this is your previous result. So let me first close it. So you can easily able to observe that at 243, at this is our current job. So I can click it and I can observe the result. So if you observe the histogram, 600 times you are getting 0 and 600 times you are getting 1 as the result, right? And you can able to observe the details that we have one circuit, and if you click see more details, you can easily able to see other details of this particular circuit. Like it is run on screen is visible or not?
Sir,
It's like 4.7 second total.
screen is visible, sir.
Right. So you can easily able to show more details on this one. And if you observe, this is your circuit, this is your custom coding, and correspondingly you can easily able to observe Q-skit coding that you can able to perform in quantum lab, open in quantum lab. So at this point of time we are only discussing composer. So come back to composer and create a circuit. Create a circuit that involves Hadamard gate and observe the outcome that you are receiving. At this point of time, we are running it on the simulator. You can able to run it on the actual hardware, but their queue is more. A number of programs you can easily able to observe that setup and run. And if you observe over here, and like this one, this is simulator. Like IBM BOGOTA, total pending job is 15. It may take some time. These are actual hardware on which you can able to run your program. Like IBM _ parse, total pending job is 674. So it might possible it will take 1 day or half day, or maybe take 2 or 4 hours to run your program. But if you want to check your result immediately, you can run it on the simulator, right? So at this point of time, you can simply run it onto the simulator. So I will give you 2-3 minutes time. You can run it. Then we will discuss another gate, and one more concept we will discuss, that is superposition. We are calling this concept as superposition. So I give you 2-3 minutes time. By 2:50 we will start with the next concept. If you have any doubt, you can ask and put your question in the chat box. So do we start with next concept, or you need some extra time?
That is done, sir. Most of the students have done, so we can continue with the next one.
Okay, right. Let me share my screen again. So whatever we had discussed, that is Hadamard gate. And it is used to generate the concept of superposition. Superposition means our qubit is in 0 state, that we can denote it by cat, as well as our qubit in 1 state. And in case of Hadamard gate, we are creating equal superposition. Equal superposition means equal chances that we are in 0 and the same chances that we are in 1. So if we are applying Hadamard it over here, we are getting these kind of things. So half probability that we are in 0, half probability that we are in 1. So we are calling this concept as equal superposition. Now what will happen if we will apply it twice? Can you able to find out what will be your result? Because this is something like, this is our Hadamard gate. And let me take our qubit is in 1 state also. So by default, on IBM computer, our qubit is in 0 state. If you want to change it into 1, apply X gate or NOT gate. So what will happen? Let me take at this point of time, I will take directly, because we had already applied this one. Then if you apply at this point of time, our qubit is in 0 state, 1 0. After application of Hadamard, we will come to this point, and you need to apply Hadamard once again. So what we will get? 1 1. That is 2. Sorry. Let me take 1 and 1 2. And this is 1 by square root of 2. So it will be 2. And it will become 0. So we will get 1 by 0. and that is qubit is in 0 state. So at this point of time, we will reach back onto qubit is in 0 state. So if we will apply Hadamard twice, this result is having no effect. So at scale, you can say it as identity matrix. Similarly, if you apply Hadamard gate on 1, we are getting this one. Apply Hadamard once again, you will get this one, and this is the status of the qubit at this point of time. So if you will multiply it, we will get 2. Simply say 1 minus 1 and 1 plus 1, and we will get 0, 1. And we can say qubit is in 1 state. So if we will apply Hadamard gate twice to a qubit in 1 state, we will get to 1. Let me show it onto the IBM computer. So first we will create our qubit in 1 state. Then we are applying Hadamard, and again we are applying Hadamard. We will not run. Now we can try out inspect and run. So at this point of time, if you observe the concept of probability, Q-sphere or state vector. So our qubit is in 1 state at this point of time, right? Because after application of X gate, we will reach into the 1. So once we apply the Hadamard gate, you can click on to the next one. Now it will show the status of the next one, that we are in 0 state as well as in 1 state, right? This red sign indicates that our amplitude is in negative direction. Then again, if you apply the Hadamard gate, so you can go to the inspector and click the next button. And then now you can easily able to observe that our qubit is in 1 state again. So we had started with 0, we had changed it into 1, and then we had applied 2 Hadamard gate, and it is coming back to 1 again, right? Now let me stop this checkpoint. Let me denote another concept that is known as entanglement. Entanglement, or you can call it as a strong correlation. If we create 2 or more qubits and they are result of one is totally dependent on the other, then you can call it as entangled bit. So initially we will take 2 qubit. Let me take it as Q0. Another one is Q1. And if I apply Hadamard gate on first one, what will happen? So it will create a superposition state. And after superposition, let me take first qubit, because it initially it is in 0, it is in 0. So it will create a equal superposition. And then apply a C0 gate. C0 gate is appearing like this one. And what is the purpose of C0 gate? That first we will discuss. C0 means control NOT gate. So we have 2 qubit, like in this particular case, we have Q0, Q1, and we are applying, we are considering it as control bit and it is target bit. So this is our control bit. This is our target bit. So if I write down initially on the input, control bit, this is input, target bit. We will come back to this circuit again. So at this point of time, we are considering we have control bit and target bit as input, and we are receiving output as control bit and target bit. So what are the possibility? If our qubit is in 0 state, target bit in 0 state, 0, 1, 1, 0. What can be the other possibility? 1, 1. Now, if our qubit is in 1 state, if control bit is in 1 state, then target bit will be flipped. Will be flipped. So what it means, if our control bit is 0, there is no change in the target bit. So control bit remains same. So you can copy directly 0, 0, 1, 1. There is no change in the control bit. But in case of target bit will change if our control bit is 1. Here control bit is 0, so target bit will not change. Here control bit is 0, so target bit will not change. Here control bit is 1, so target bit will be flipped. So we will write down 1 over here. Here control bit is 1, so target bit will be flipped, so 0. In brief, I can write down it as, if it is 0, 0 in first case input, so our output is 0, 0. If our input is 0, 1, first is denoting the control bit, so our target is 0, 1. There is no change. If our control bit is 1, 0, so our target bit will be 1, 1. This is our output. If our input is 1, 1, then output is 1, 0. And we can call this as the control bit and this one as the target bit. I can denote it by matrix notation 0, 0, 0, 1, 1, 0, 1, 1. 0, 0, 0, 1, 1, 0, 1, 1. So if our input is 0, 0, input is 0, 0, what is our output? 0, 0. I can write down 1. If our input is 0, 1, this is our input 1, 0, 1. So output is 0, 1. So I will write down 1 over here. If our input is 1, 0, input is 1, 0, output is 1, 1. So 1, 1. If our input is 1, 1, this one is our input. So output is 1, 0. In the rest of the cases, I can write down the 0. That it will not be possible. Now this matrix can be used for C0 gate. Now come back to the previous circuit that we are creating and we will discuss what the actual outcome. Now what we are doing, we are taking 2 qubit and on the first we had applied Hadamard gate and then we had applied C0 gate. And then we will discuss, we will measure it, right? So these are our control bit basically. This is C1, C2, oh sorry, C0, C1. Now what will happen at this point of time? After application of Hadamard, we will get this one. And second qubit is in 0 state. So at this point of time, our quantum system is in this state. First qubit, and usually we will denote it by tensor product. So those who are not familiar, they can consider it as something like this one, 0, 0, 1, 1, 1, 0, sorry. Combine this with this one. So this is our first qubit, this is our first qubit, tensor with the second one and 1, 0. We will get this one. We will discuss the meaning of tensor also. Then we will apply C0. So at this point of time, we have this status. And this is our control bit. This is our target bit. And we had applied C0 gate. So if we will apply C0 gate, what will happen? If control bit is 0, so what we will get at this point of time? If control bit is 0, so target bit will not change, 0, 0. If control bit is 1, so it will flip. So at this point of time, we have a system with this state. So if we will measure the first qubit, second qubit automatically change into the outcomes. Like if our first qubit is in 0 state, then the second will collapse into 0 state, because either we will get 0, 0 as the result or we will get 1, 1. If first qubit we will measure in 1 state, then second also converted into 1 state. So these two qubit, first and second qubit, are giving us highly correlated result. Means if outcome of first is coming out to be 0, definitely outcome of second is also 0. If outcome of first is 1, then outcome of second is also 1. So we can call this as related qubits or entangled qubit. And this concept is used in quantum cryptography. So if you have two qubit at a far distance, maybe 10 lakh kilometer distance, and if you measure first qubit, if its result is 0, then second qubit result is also coming out to be 0 if they are entangled using this relation. If first qubit is 1, then second qubit is also 1. Now you can able to create the program for entanglement. What we need to do first is we need to create two qubits. So I will take Q2. Then I need to apply. So I will remove these gates. I need to keep Hadamard gate on the first one. Then apply C0 gate from first to the second. And this is the third gate, H, X, and then we will get the C0 gate. We can drag it. Right, and let me start with the inspector case. What we will get initially, what we are getting as the state vector. If you observe over here, our result is 0, 0, 1, 0. Because in case of classical computer, rightmost bit is considered as the first qubit. In quantum, what we are taking Q0, then Q1, Q2, right? So this 0, 0 and 1, 0 means the leftmost, or you can say first qubit is in 0 as well as 1 state, and second qubit is in 0 state. Now if you will go ahead, you can easily able to observe our result is in either 0, 0 or 1, 1. This is 0, 0 and this is 1, 1. No result in 0, 1 and 1, 0. Now, whenever we will measure it, you can observe over here. It is falling into 1, 1 because this is the only one sort. And if we will run it 1000 times or 122 times, we can able to observe our result. And you can see the result over here. It is completed. Oh. Okay, let me check it once again. So it is not showing the result of second qubit because we had taken one qubit as the classical one. So first you need to close it, inspector, and then you will take 2 qubit. And let me measure the second qubit also. And then we will set it again and run it again. Go to the jobs and you can find out the result over here. So you can see over here, it is either showing 0, 0 or 1, 1. Right, so 600 time it is showing 0, 0, 600 time it is showing 1, 1. So there is zero outcome of 0, 1. There is zero probability that we will get 0, 1, and there is zero probability that we will get 1, 0. Right, so half of the time we are getting 0, 0, half of the time we will get 1, 1. Now I will give you a task. You can try it out. And you can take 5 minutes time. And let me give you one question. Let's suppose you want to create this kind of entanglement, 0 1 plus 1 0, and you need to use only Hadamard gate and C0 gate. Right? You can try it out this one. If you have any doubt, we will discuss it. And after 5 minutes, we can discuss this concept and move ahead. If you have any doubt so far, you can ask your question. So you need to create 0 1 plus 1 0, equal position, equal superposition. So I'm sending a link of that contain the material for IBM Quantum Composer. So you can click on that particular link and you can find out some more programs over there.
We've not got the link.
I send in the chat box. You can just go through the chat box. Whether you had received?
Okay, just because my network is very weak.
Okay.
I have not got yet. Okay, I think someone has got. Keep dropping.
Okay, let me send it once again.
Yeah, we got it.
Okay, great. So had you created these kind of entanglement, 1 by square root of 2, 0, 1, minus 1, 0.
So can you show how to create it? Like I got.
Okay, let me try it out. Because you need to use Hadamard gate, C not gate, or something like that, or X gate. So this is known as anti-relation. Anti-relation means if in first one I am getting 0, so in the second one I am getting 1. If first qubit is measured as 1, the second qubit is measured as 0. Now let me try it out. Let me apply X gate on it. So first qubit is in one state, right? Then let me apply Hadamard gate over. So what will happen after application of Hadamard? What we will receive as this one and 0. So first qubit, what we will get 1 by square root of 2, 1. And the second one we will get minus 1, right? So I can denote it by 1 by square root of 2, 0, minus 1. So at this point of time, first qubit is in this state. And if we will apply C naught from first qubit to second qubit, what will happen? At this point of time, our complete system is like this: first qubit is 0, second is also 0. So 0, 0, then 1, 0. Right now we will apply C naught from first to second qubit. So if first qubit is in 0 state, that is control bit, so target bit will not change. So this is we are getting at 0, 0, and minus over here this will be flipped. So this is one of the another entangled state. Although we had not received the desired one, but this is also one of the 4 maximum entangled state. There are 4 maximal entangled state for you can able to form using 2 qubit, right? So what other option you can try out? Let me try once again. So by this we had observed this one. Let me try it out. 1, 0, 0, 1, sorry, minus 1, 0, right? So what other option you can try? That we need okay, I will send you the solution of this one. Probably you need to apply X and X on the second one, right? So you can try out this option. If you will not able to construct it, we will discuss it.
Okay.
Right. So what we can discuss now is what will happen or how qubits are combined if we have more than one qubit. Like if our first qubit is in 0, 1, that is qubit is in one state. So there is a concept of tensor product that we will code. And let me take second qubit is in also one state. So how we will take their tensor? Like if we have first one is A1, B1 and second one is B1, B2, what we can combine it as A1, B2 and A2, B1 and just simply multiply it. What we will get? A1, B1, A1, B2, A2, B1, A2, B2. Over here, if you observe, this is A1. So you can think it as like this one, 1, 0, 1. So if I multiply 0 inside, so I will get these results. So whenever I take one qubit and I will take tensor with another qubit, I will get 4 entries, and this entry is denoting 0, 0. This entry is denoting 0, 1. This entry is denoting 1, 0. And this entry is denoting 1, 1. Similarly, if we have n qubits, you can easily able to observe. If we have n qubit, so we have these kind of entries. It might possible this is alpha, beta, some probability in 0, some probability in 1, alpha 2, beta 2, and alpha and beta n. Let me take it as like this one. So how many entries we will get? 2 raised to power n entries. Right? So this is the way how we can able to combine more than one qubit. You can observe these kind of concept using Hadamard gate also. Apply Hadamard on both one and what you are getting. So if you apply Hadamard on both one, so at this point of time, we will get this one. At this point of time, we will get the same one. And it can be represented by this one. The same one can be represented for second qubit. And if I ask you what is the state of the system, if you will measure it, measure first and second qubit. So at this point of time, our system is in this state. So you can take their tensor 1 by 2. So 1 into 1 by 1, 1. So I can get 1 by 2, 1, 1, 1. And I can write down it as 1 by 2, 0, 0, 0, 1, 1, 0, 1, 1. Because this is 0, 0, this is 0, 1, this is 1, 0, and this is 1. So those the students, those who are interested in quantum machine learning, let me tell you few concepts, little bit how it will go. So you can consider it as there are 4 things. One is classical data. Second one is classical algorithm. And third one is you can say quantum data and quantum algorithms. So there are 4 kind of concepts you can say. So let me denote it by CC. Let me take data over here. Let me take data, whether it's classical or quantum. And let me take whether our algorithm is classical or quantum algorithm type. Right? So we have 4 options. This denotes, the first one is denoting the classical data, classical algorithm that you are doing in classical machine learning. and this is quantum data and classical algorithm. Last one you can easily able to say quantum data and quantum algorithms. And the last one, CQ, that is classical data and quantum algorithms. So quantum machine learning basically deal with these kind of problems, that you have some classical data and you will apply some quantum algorithm to speed up your process. And for converting classical data or for using classical data into quantum algorithm, you need to encode your data by using the concept of that we had discussed today, that is like superposition or entanglement. These concepts will be used, right? And there are some encoding techniques you will be used, like amplitude encoding or data encoding, and there are more concepts also like rotation encoding. Those concepts will be used, right? So for using classical data into quantum algorithm, you will require these kind of concept, that you need to first you convert your data into quantum states. So quantum state concept today we had discussed, and using some encoding scheme. And then you can use your quantum algorithms to enhance the performance of your algorithms to find out some patterns, right? So last concept I'm discussing today, that is how the measurement probabilities are coming. It may take near around maximum 10 minutes. So last concept I'm telling you about measurement. What is the meaning of measurement? Like sometime we are doing these kind of things. So we are saying measurement in G basis. So it might possible you want to measure in Hadamard basis also. So this is also one of the basis. So if you want to measure in Hadamard basis, just apply Hadamard before G basis, right? So diagrammatically, if you represent it as 0, 1, you can consider it as 1 by square root of 2, 0, 1, this one, and this one as the negative one. Sorry, in this direction, basically. 1 by square root of 2, 0 minus 1. We will also denote it as minus. This is also denoted as plus, right? So if we will measure our result in Hadamard basis or computational basis, what we are getting? So far we are measuring it in G basis. That is either we are getting 0 or 1. So how these measurement concept will take place? Let me take a state psi 1, and we had already discussed this one. That is we are getting the result after the Hadamard operation on 0 state. So how we are getting the probability of 0? You can take inner product. Inner product means inner product of vectors. Those who are not familiar, you can take V as a vector. So it is denoting by this concept. So here we will take this one, and this concept is known as cat notation. And if I write down this one is bra notation. And it is obtained by taking conjugate of the transpose of the matrix. So we will discuss it. Let me take first this one. So if I want to take bra notation of this one, so what I will take, it will denote it by this one, and I will take transpose of this one. Transpose of this 1 1 is 1 1, but it is 1 row and 2 column. And if there is something like, let's suppose 1 plus iota, So we will get over here 1 minus iota by complex conjugate concept, right? So here it is 1 1, so we will get 1 1. So you can take 1 by square root of 2 1 1, then multiply it by 1 and take its scale. So you will get 1 by 2, then just simply multiply it 1 and 1 2, and this is square root 1 and 1 2. So what you will get? Now this will be the result if we are measuring in Hadamard basis, because this is the value of the Hadamard. If you want to measure in G basis, it will be 0 over here. So if you want to measure it in 0 basis or computational basis, we will take 1 0. If you want to take Hadamard basis, we will take psi again, right? So what we will get to, let me take it once again. This is not 1 by square root of 2, it is 1 by 0. And we will get 1 by 2 and just simply multiply 1 and scale. And what we will get? Half. So this is the way how we will get the measurement. So if we want to measure what will be the result in 1, we will take 1. Right? So this is our state in bra notation. So what we will take 1 by square root of 2, 1, 1. And qubit is in one state, 0, 1. And if we will multiply, we will get 1. But let me take a qubit, same qubit, and you want to measure in plus basis, what we will get? So our qubit is again 1 by square root of 2, 1, 1. Plus means again 1 by square root of 2, 1, 1. So I will write down 1, 1. Right? And let me take 1 by 2. Because if I multiply it 1 by 2, I will get, and this is 1 plus 1, 2, and I need to take its scale, it's 1, and I will get 1. So if I measure our quantum state 1 by square root of 2, 1, 1 in plus basis, I will get the probability 1. If I measure our qubit in 0 basis, we will get half the probability in 0 state, half the probability in 1 state. Right? So if you have any question, you can ask. Otherwise, it is over from my side. Let me share one link with you. If those who are interested to study on IBM Quantum Lab. So those who are interested to learn about quantum Qiskit, they can go with this link. And one more option I am telling you how you can proceed. Let me share one again my screen. Yeah, so you can go to all jobs that we had run and go to jobs and view all jobs. So if you click on this one, any of the jobs, you can find out the detail over here that you can run equivalent Qiskit coding. So you can open in Quantum Lab and you can able to run it. So over here, these kind of codings will be used from Qiskit, import quantum register, classical register, quantum circuit, import PI from NumPy, and then these kind of circuits will be used. Right, so these are the kind of syntax you can refer from the equivalent Qiskit coding. Yes, any question?
A very good afternoon, sir.
Hanji, good afternoon.
Sir, this is Dr. Anand Sharma.
Okay.
Yes, there is a generalized question that quantum computing, this domain of only on big companies like IBM, Microsoft, Amazon,
Right.
So, what's the future of that quantum computing? Must be so much popular that it can be, at any small IT companies, they can also utilize this the power of quantum computing.
So it might possible. It's something like we are using quantum computer online today. So might
Yes.
possible after 10 or 15 years, maybe 1000 qubit quantum computer will be available online and you can use the facility. And if I'm not wrong, there is a concept, blind computing concept is there. So by that way, you can use some quantum hardware like we are using on the quantum system, and they are unaware about this one if they are providing us the facility what we are doing on that particular hardware. So
any company quantum computing lab in India in public sector?
At this point of time, no. Although some theoretical research are going on in some ICERs, Mohali, or you can say ICER Bangalore, but I'm not aware about that kind of thing. But you can, as a computer engineer, you can able to carry out your required work in IBM Quantum Qiskit.
Yes, yes.
Right. Oh,
It needs a huge investment.
Yeah.
It needs a huge investment to establish the quantum lab.
In addition to huge investment, because these quantum circuits or quantum hardware are error prone basically, and they will require very low temperature.
Okay. That
so
is
that's why it's not possible at every place. So they will require a lot of care. If you will go through this Qiskit also, like we are running some program that superposition. We are getting 0 500 time, 1 500 time. But if you will run it on the actual hardware, so might possible that you will get the result 0 480 time, 1 520 times due to some kind of error in the hardware. So whenever you implement some gates, so there are chances that you will get some errors.
The performance varies, right?
Yeah, you can say your performance will vary little bit, but not too much.
And is it possible the quantum computing can be utilized for the 5G or 6G networks?
5G, because at this point of time you cannot use it, because actual hardware, if you observe about IBM, I think 127 qubits is available, but you can only able to use 10 qubit, 16 qubit up to like this one for public use.
Underutilization.
Yeah, because they are carrying out research on this one. So 127 qubits hardware is not available at this point of time. So for carrying out any kind of networking, I think you will require more qubit as well as more quantum hardware resources like quantum repeater or something like that.
It's very a nascent stage.
You can say it's very initial state, but is not too far away also.
Yes. Why not, sir? Since you are in quantum computing for the quite long time, so I think you are the most appropriate person. So we can have a discussion on that.
Right. You are most welcome at any point of time.
Yes, sir. Thanks a lot, sir. It's it's very new field which we are entering into. There is quantum computing, especially with the machine learning concept, and hopefully it will improve the working and the efficiency or the performance utilization of the quantum computing.
Right, sir. Right.
Sir, I'll have one question.
Yeah.
Regarding quantum machine learning, what do you think are the challenges of quantum machine learning? I think you delve into the quantum machine learning at the end of your presentation. So just wanted to know the challenges. Which
although this is not my area of interest, but what you can do is major interesting thing, major problem you will face is data encoding. Like at this point of time, we have less number of qubit. So to represent large amount of data into those qubit is a big challenging task.
So the data processing will be faster in quantum computing.
There are two things. One is you need to convert your classical data into quantum state representation.
So that's the biggest challenge, right?
That is the one of the biggest challenge, and currently research is going on how we can able to represent it efficiently. What are the better way, whether it is data encoding or amplitude encoding and all those type of things. Then so once you are able to encode that into some of the encoding scheme, then the things will come which quantum algorithms you will apply. So there exists some algorithms like quantum supervised learning algorithms are also there. There is variational parameter circuit kind of concept is also there, which can be used as a classifier also. Just something like you are using classifier in classical machine learning. So there is a concept like variational parameterized circuit. So you will create circuit but give some parameter on that one, and based on that you will train your data.
Okay, thank you. So no one has actually implemented any algorithm like simple supervised logistic or linear regression in the quantum?
No, there are work is going on, and many people are working on it. And if you will go through the research paper, you can easily find out some work in this area.
Okay. Thank you, sir.
So participants, any other queries from your side? Okay. Thank you, Dr. Ajay. It's very new area where you have given your the feedback or the learning, new concept and online simulation. We can carry out the experiments also. So it's very good to hear from you, and hopefully in our next 3-4 years, this quantum machine learning will develop just like a deep learning has developed, because I heard machine learning in the year 2015 and now it's been so popular. Similarly, hopefully the quantum machine learning will be next 5 years or 10 years, it will develop in a separate and new field, emerging field.
Right, sir. I think it's not too far away. I think as the number of qubits will be increased and it's available online, then more and more people will carry out some kind of research work in this. Any doubts, sir?
We are winding up the session. We are just winding up the session.
Okay,
hopefully
right.
the query has been resolved.
Okay, right, sir.
Thank you, sir. Thank you.
Okay, thank you.